anyone heard that word before? Yeah, I mean, it's one of those words that you've probably heard, and you probably associate it with what? I mean, maybe science. Maybe your answer to that is I associate the word isotope with science. Anything else we kind of associate the word isotope with? It's the name of Springfield's baseball team in The Simpsons, the Springfield Isotopes. Is that a hand or that's just got a pencil? Okay, well, we'll talk about it. I want you to recall, if you will, the periodic table. Look, we have one right here. And I grabbed an element at random from the periodic table, and I want you to quickly, on your sheet, I'm going to give you 3 minutes, tell me what you can about lithium here. Specifically, what you can tell me about its subatomic particles. So you got 3 minutes, use them. What are the subatomic particles again? Anyone? Bueller? Yeah. Great. So, this has got not all the assignments. I think it's got all the notes for our first unit. So you'll need headphones if you want to watch through the lesson. You can just fill it in and fill it out. That's totally fine. If you want Teams in my classwork, you'll see I posted module 1. And I posted the first 4 lessons, but the goal should just be 1 and 2. And I'll keep you guys sort of on track with where you should be. So, maybe fill a little board here. What's the date? Today's been the 3rd.
Yes. Today's the 3rd.
Yeah. So today, if you just work your way to that lesson, all right, talk to me. Subatomic particles. What are the 3 subatomic particles? Protons, neutrons, and electrons. Good. Protons, neutrons, and electrons. Which of this is easiest to fill in if we're looking at the periodic table? Protons. And why is that? Yeah, the atomic number is literally the definition of how many protons there are. Wow, that highlighter really did not show up very heavily. Is that any better? Marginally. Okay, so the atomic number tells us how many protons, so lithium always has 3 protons. What else can we determine relatively easily? Yeah, why is that? Yeah, in a neutral atom, the number of protons and the number of electrons must be equal. How do we know that? Yeah, we know that in general, in things in nature, have a charge of 0, right? They're not charged. What about the neutrons? How do we determine that? What is it? What's the number?
It's the atomic mass minus the atomic number.
Yeah, very good. Is the atomic mass minus the atomic number, which is to say, it's the mass minus the number of neutrons, right? Or protons, rather. And so the mass in this case, should I write 6.941? We write 7. Why wouldn't I write 6.941? We round it. Why do we round it? I mean, we know that we don't have how many neutrons? 3.941 neutrons, right? Because that's hard to picture. So we do this and we get the number 4, right? But, bless you. But my question is, why isn't this 7 exactly? Why is it 6.941? Shouldn't it just be 7? Okay, that's a good answer. Electrons do have a little bit of mass, right? Electrons got a wee little bit of mass. And so by virtue of having a wee little bit of a mass, electrons are going to change that number, which means that the number should be less than 7? Do electrons have negative mass? No. So shouldn't the number be 7.00 something? But it's not. So why is it 6.9? Well, as it turns out, the answer is that the mass is an average. It's an average. Now we said that this is always true, right? By definition, if something is lithium, it must have 3 protons. Can we change this? Yeah, right? We can take electrons away from lithium. In fact, very commonly, lithium will lose 1 electron and take a charge of +1. And what about neutrons? They can also change. Some lithium atoms don't have 4 neutrons. Now, as it turns out, most of them have 4 neutrons. Does that make sense? But some have more, and some have, fewer. And just looking at the average, what's more common? Having more than 4 or having fewer than 4? Yeah, fewer, because the average isn't quite 7. It's a little bit less than 7. Does that make sense? Which means that the average, the median lithium atom would have 4 neutrons for sure. Does that make sense? Like, that's the most common value. The modal value would be 4. But the average is a little bit less than that, which implies that it's a little bit common to have some that weigh less. So, lithium doesn't always have 4 neutrons. As it happens, lithium nuclei can be stable with either 3 or 4 neutrons. If you try to pack any other number in there, it won't be stable. Does that make sense? If you try to make a lithium nucleus with 2 neutrons, it'll fall apart rather quickly. If you try to make it with 5 neutrons, it will fall apart rather quickly. You can do it, but it won't be stable. But as it turns out, you can make a stable nucleus with 3 or with 4 neutrons. For you students, Ruby's putting together, do you have a binder for this course? If you do, we've got notes here for you. If you don't, I'll send Ruby on down to the science office to grab you a binder, and she's getting it made up for you. Great. Do you know where the science office is? Not mine, like the science office down the hall. If you go in, on your right, you'll see a shelf, and there'll be blue binders in the bottom left. If you ask the teacher there where the binder's on, they'll show you. Cool. All right. So we show this in 2 different ways, by the way. We refer to this as lithium 3 or lithium, I lied. It wouldn't be lithium 3. If lithium had 3 neutrons, what would it weigh? Lithium had 3 neutrons, what would it weigh? Good. So we'd show this as lithium 6 or as lithium 7. And we'll make a quick note here. That is 3 protons, 4 neutrons. And this is 3 protons and 3 neutrons. Does that make sense? And you'll see it written that way, or you'll sometimes see it written this way. You'll even sometimes see it written this way. They all mean the same thing. Does that make sense? You'll see all of these as ways that we write that. And we call these isotopes. So different versions. Awesome, thank you. Of an atom with different numbers of neutrons are called isotopes. Does anyone know what iso as a rule means as a prefix? So it means steady or the same or whatever. So in this case, we're talking about it being the same atom, but different versions of it, different masses. So isotopes have different masses. And that's obvious because neutrons have mass. So they have different masses, but the same atomic number. which means that isotopes are the same element. All right? Lithium-6 and lithium-7 are both lithium, and you can find them both in nature. Now again, if we look at the average mass, which is more common, lithium-6 or lithium-7? Lithium-7. Is it a little bit more common or way more common? Way more common. How do you know? Yeah, the mass is almost 7, right? The average mass of lithium is so close to being 7 that we can just round it to 7, right? But still, it's not exactly 7 because every once in a while, as it happens about, a couple times out of 100, if you grabbed a random lithium atom, you would find one that has 3 neutrons instead of having 4. Does that feel okay? That feels not too bad? Now, there aren't always just 2 stable isotopes. The later on in the periodic table you go, some of them have many stable isotopes. There's a great Wikipedia table you can go look at that has all of the stable isotopes of all the elements, and you can see that you get up there on the periodic table. Sometimes there's quite a few. Hydrogen is interesting. Hydrogen has 3 isotopes. Looking at the periodic table, what is the most common isotope of hydrogen? The most common is what we call hydrogen 1. And it's called that because what's the average mass of hydrogen? 1. Hydrogen 1 would have how many protons, how many neutrons? Hydrogen 1 would have how many protons, how many neutrons? Yep. 1 proton and 0 neutrons. All right. And if we were to draw that, it would have a proton in the middle. And how many electrons does a hydrogen atom have? Yeah, just 1. Okay. What about hydrogen 2? What would that look like? Yep. Very good. It would have 1 proton and 1 neutron, making its total mass 2. Very good. And how many electrons would that have? Yeah, very good. Nothing changes there, right? Because the electron is balancing out the proton, but this one would have a neutron here as well. That, occurs to me, does not look like a nice nucleus. I'm going to redraw it. Proton and a neutron. Still 1 electron, but now a proton and a neutron. And finally, and this is given a name, actually. You can call it hydrogen 2, but it's common enough that we call it deuterium. Deuterium. In nuclear reactors, they use water, where the hydrogen they use to make the water is not regular hydrogen, but what we call deuterium or hydrogen 2. And so the water is literally heavier than water would normally be. Water is normally an oxygen, which weighs how much? Roughly? 16. And it's 2 hydrogens, which weigh together how much normally? 2. So water normally weighs 18 atomic mass units. But if instead you make the water from deuterium, it wouldn't weigh 2. It would weigh 2 twice, which is 4. And so the water weighs 20 atomic mass units. And so for a variety of reasons involved in making a nuclear reaction happen, they use heavy water. But heavy water is literally heavier than regular water because it's made with heavier hydrogen. Sorry? No, that's different. That's just like with a gelatin or something. This, you wouldn't really notice it. It's still just water. But if you were to weigh it against sort of regular old tap water, it would be quite a bit heavier. What is the difference percentage-wise between 20 and 18? I don't know, whatever 2/18 is. Roughly, 24%. And then, what if instead of 1 neutron, we gave it 2 neutrons? Now it would be hydrogen 3. This is also given a name. Does anyone know what it is? You might have heard of it. Excuse me. This is interesting because it glows bright green. It's very expensive. It's incredibly rare, so it's hard to make. But this was used in like military sites because it glows green with absolutely no energy needed or anything like that. So you could use it in like a scope and it would always have a bit of a green to it, or really expensive like military watches that they want to always have a glowing back face that don't need a battery or anything. As batteries have gotten cheaper and easier to make, these things have become less common. Yeah. Nope. It's called, you may have heard of it, tritium. Anyone heard of that before? Tritium. But tritium is a hydrogen atom that has 1 proton but now has 2 neutrons. And of course, how many electrons would this have? Still just 1. Now, bless you. Would the mass of this be exactly 3.00000 infinitely? No, because what is still the mass to account for? Electrons. And then, okay, listen, look at me. We're not going to teach you like the quantum mechanics in this course, but ready? Everyone has seen this before. What's that? E equals mc squared, that's famous. From whom? Sorry? Einstein? Yeah, Einstein. All right, this is, just listen, this is just something else you have to know. Basically, this says that energy and mass can be converted from one to another, all right? And in fact, energy is just equal to mass times the speed of light squared. You don't have to know too much about that, except to say, as weird as this is, every time you speed up or slow down, you actually gain a little bit of weight and lose a little bit of weight. As your velocity changes, your mass changes. At the scale of U, that is completely unmeasurable, but at the scale of atoms, it actually makes a difference. So the fact that atoms vibrate and rotate and move actually changes their mass, all of which is to say, when you're talking about the mass of an atom at that scale, once you get a few decimal places in, things get weird. Good news, you don't have to know any of that for this course, but I'd just like to mention it as something to be aware of. If you're ever wondering, why can't I just take the mass of an electron and add it to the mass of a proton, add it to the mass of a neutron, and it never seems to quite exactly line up with anything? As soon as things start moving in those decimal places, the masses start changing, and stuff gets weird. Does that make sense? Cool. Again, for you, did you get your notes? There's computers in the back, so if you go into the Teams class for that, go into classwork, you'll find, oh, you're on it. Awesome. Cool. So you can fill that in. There's a video if you want to watch it. If it's something you're pretty comfortable with and you just want to follow through the note itself, that's fine. But you should be able to find it there. Okay. So let's look at this as an example, and I want to show you where that number on the periodic table comes from. If we look at lithium, these are the actual 2 isotopes. We said that in the previous note, right? Lithium 6 and lithium 7. So if we want to know the average weight, well, this is how much the first one weighs, and this is how much the second one weighs. And if you want to find an average, what do? Yeah, except, to be clear, are there 2 lithium atoms in the universe? No. In fact, there are more than you could ever count. Does that make sense? So you can't just do the old atom up and divide by 2, because that would imply that there's only 2 atoms out there. Does that make sense? When really there's lots. In fact, we know that there's countless, but we know that for every 100 of them, how many weigh this much? Well, about 7.6. And how many weigh that much? 92.4. In fact, what you have to take here is called a weighted average. Does that make sense? A weighted average. So these are the stable isotopes of lithium. You can see this is by far more common. This is less common. You'll note that they still aren't exactly and will never be exactly and that's because of electrons, which have mass, but it's also because of what we talked about there, those quantum effects. And again, you don't have to dig into this too much, but just be aware that you should never expect these to be precisely whole number values. Does that make sense? But okay, there we are. How do they figure this out, by the way? Do you know? Scientists actually have a machine called a mass spectrometer, and a mass spectrometer is a little machine that we can use to spin something around really, 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 really fast, and then shoot individual atoms off, and we see how much they bend as they make their way across a path, and you can use that to see how much those particles weigh. And a mass spectrometer is more expensive than we can have in this setting. A good mass spectrometer would cost, I don't know, $300,000-$400,000. That's a lot of money, but like we had one at Brock that we got to use. So it's not like something that like only exists like, in CERN or something, and you can use that to figure out how much particles weigh. So in this case, if you take a sample of lithium and run it through a mass spec, you'll quickly see that you get a peak at 6.0151 and a peak at 7.0160, and that tells you you've got two stable isotopes. Furthermore, you can see how big the peaks are, and that will tell you how much those are. Does that make sense? This is something that can be done with a sophisticated piece of lab equipment, but a piece of lab equipment that's been around since the 50s, not something that's brand new. So, how do you calculate an average? We have to find what we call a weighted average. What's it mean to say a weighted average? Well, if we could do this really quickly, actually. How old is everyone in this room? I am, okay, ready? Let's do this. I am 41, but I'm the only person in here who's 41, yes? How many people in here are 16? Hands up. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have 9 people who are 16. And then how many people are 17? 1, 2, 3, 4, 5. Anyone 18? Cool. Anyone older than that? 19, 20, 21, 22, 23? Okay, we're good. If I wanted to take the average of this, what I could do is I could do 41 plus 16 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 plus 16. Right? I could keep doing that. Yes? Okay. And then plus 17 plus 17 plus 17 plus 17 plus 17 plus 18 plus 18, and then divide by all that. Is that the most efficient way to do that? No, what we could do is we could do 41 plus 16 times 9 plus 17 times 5 plus 18 times 2, right? And then we just divide it by how many. Does that make sense? And if we wanted to, we could even go one step further and figure out what percentage of people are each of these ages. Does that make sense? So here is the formula to take a weighted average. And you're going to see a little bit of math symbols here, but then we'll explain what they mean.
Excuse the interruption.
Yeah.
We have ONT in guidance.
Yeah, you bet. So to find a weighted average, if we want to know the average of these, where for every 100 atoms, 7.5 of them weigh, 7.6 of them weigh this much, and 92.4 of them weigh that much, here's what you can do. You're going to take the sum. And does anyone know what Greek letter that is? Very good. That's a sigma. And sigma means take the sum. And what's another way of saying sum? Add together. Does that make sense? So we're going to take the sum of the mass times the abundance as a percentage. But, well, we'll talk about that in a minute. That's it. So what this means is, for each isotope, multiply its mass by its abundance, then add all those together. And I think this gets easier if we do an example. Is that fair? So take a minute, write that down. Can everyone read that, by the way? Sorry, I'll use a darker pen. On my screen, that blue is reasonably dark. And I see that up on my failing projector, it is not dark at all. Sorry about that. Do I need to rewrite it, or are we okay? Can we read that? You can tell me now. I'm here for you. I work for you. I mean, not in the sense that I will ever do anything you tell me, but in the sense that, except maybe you actually. I feel like I've been hard enough on you that maybe just once, like one time, you should tell me something and I'll do it.
I mean, that's only fair. I do it.
I mean, in fairness, you also give me a very hard time.
Okay, you give me a hard time too. So.
Yeah. Now, the other thing I'm going to show you is something that we do frequently in science. We use this symbol. What is that? Well, it's just a line, but we use it when we say it aloud. They'll say bar, but that just means mean, which is another way of saying average. So if we want to know the average mass, we could say like that's the average mass. But if we want to know the average temperature, we could show it like that. So that's a short form that you'll see a lot in science. Does that make sense? When you see something with the line over top, that means that we are calculating the average. Can we do this? Math's pretty easy. You only need a calculator. There's some back there if you need. And let's look at the first isotope. The first isotope, lithium-6, has a mass of what? Has a mass of 6 point what? Probably better for you to look on your sheet. I'm going to zoom in here. But what's the mass of the lithium-6 isotope? 6.0151. And what's the unit on mass? Yeah, we can use AMU, or we can use the mu. And what percentage of isotopes have that value? Good. Now, you have to work with this either as a decimal or as a fraction. I like to do percentages as fractions because what does percentage mean? It means out of 100. If you prefer to convert that to a decimal, I just feel like people screw it up all the time. What is 7.59 as a decimal? 7.59%. It would be decimal 0.759. What do people accidentally do all the time? They don't put the zero, and that would be 75%. Whereas, if you always just make a percentage as a fraction out of 100, which is, by the way, what percent means, you'll never get it wrong. I don't know why we don't teach it this way. My whole life, every teacher was always like, oh, convert that percentage to a decimal. And, you get it wrong 10% of the time. You make it a fraction over 100, you know what percentage of the time you get it wrong? 0. It's just easy. Okay, now, what's the other isotope? Lithium 7. And what are we going to do with that one? What's the mass of it? 7.0160. Okay. What's the unit on that? Atomic mass units. And what percentage is that? Well, it's got to be 92.41. And how do I make that a decimal or a fraction? I can put it over 100. And then what am I doing with these two calculations? Yeah, the sigma tells us that we're going to add those up. That's taking a weighted average. And now if you just do that carefully in your calculator, and listen, I'll demonstrate up here. If you aren't already in this habit, get in the habit of just typing things in your calculator all at once. All right? Use brackets, all right, if you need to. 6.0151, all right? And then we're multiplying that by what? 7.59 out of 100. By the way, what does that symbol mean? You could use the fraction button if your calculator has it, but of course, what's a fraction just doing? Dividing. That's right. I don't have a division symbol, or I'd put it there. But yeah, I like that. And then what do? Add. Oh, God. Golly. Okay, and then what? Point. Yep. Times. Yeah. By the way, that bracket isn't actually doing anything, but it makes me feel safer. So I put it there. That's the truth. It's mathematically, that bracket is accomplishing nothing, but it makes me feel like that percentage is its own thing. And sometimes in life, if you need the safety blanket of a little bit of brackets, I just say go ahead and do it. Now, before we do anything, is this going to be closer to 6 or closer to 7? 7. In fact, according to the periodic table, what should it be? What should it be? According to the periodic table, what number should I get here? 6.941. Let's see if that's what we get. Now, my stupid calculator stops at 2 decimal places, but yours might give you more. 6.9400. And the reason we didn't get exactly what the periodic table says is because there's a couple other isotopes that aren't stable, and we didn't bother putting them in here. Does that make sense? But that's okay. There we go. So we get 6.9400 atomic mass units, which almost perfectly agrees with the periodic table. Does that make sense? As math goes, how's that feel? Not too bad? Honestly, that's as hard as the math gets in this course. Yeah, really. If you can do that, you can do all the math in this course. Did we just do that successfully? Great. Chemistry, not a ton of crazy math. We get like one formula, like in Unit 4, that you'll have to like do some algebra with, and it's literally like the easiest formula ever. Math and chemistry, it's all just ratios. If you can multiply and divide, you can do chemistry. Really, if you can bake, you know how to bake? I made pasta last night, and my recipe says that for 2 cups of flour, mix it with 3 eggs and like a teaspoon of oil. But I had like a bunch of people in the house, so I need to make twice as much. So instead of 2 cups of flour, I used 4. Instead of 3 eggs, instead of 1 tablespoon of oil, I used. Congratulations, you can do grade 11 chemistry. That's it. That's this whole course, I promise. Sorry? Depends on what I'm doing, but if you're making pasta, listen, let me tell you right now. The mistake everyone makes when they're making pasta, anyone ever make homemade pasta? Like the noodles itself? When you make the noodles, the mistake everyone makes is it feels really dry when you start, so you always add more liquid, and then when you start rolling it out, it's sticky as hell and crazy and awful. So what you have to do is when you're mixing the pasta, it's going to feel crumbly and dry and crazy, and you just have to knead it for like 8 to 10 minutes, and it gets to a consistency that you can work. And with that one, you will outsmart yourself every time and start adding liquid. Then when you start rolling it, it'll stick to itself. You'll have to add flour. Before you know it, there's flour everywhere. Before you know it, the dog has gotten into the flour bowl, and now the dog has flour all over its face. Hypothetically speaking, maybe this has happened to me. I don't know. Anyway. Friggin' Arlo. Dog's an idiot. Anyway. He's cute, though. He's very cute. Kind of like me. Cute but stupid. Okay. So, I am cute, though. All right, I want you guys to try the next one. Iron. By the way, let's look at the periodic table. Where's iron? Yeah. So can you check your answer when you're done? Yeah. But how many isotopes do we have to deal with here? 54. But how many isotopes? 4. Now, is that annoying? Is the math actually any harder? No. What are you going to do for each isotope, just like we did here? You're going to take the mass and multiply it by the abundance, and you're going to make sure you work with that as a percentage, right? And then you're going to do that for the next isotope, and the next one, and the next one, and what do you do with all those? Add them all together. And I think you should do it in one step on your calculator, all right? So get to it. There's that. For you, we're finding everything on there okay? Do you guys have any questions? Again, this lesson fairly straightforward, but I really want to encourage you. Anytime I'm teaching here, and you guys are working from a package, don't be shy. If you don't know what something is, come tap me on the shoulder. I can get these guys working on something and help you out, all right? I know it's a weird environment for us. If you just want to kind of walk around the room and just see that people are, vaguely calculating what to do. I'm going to throw coffee in my cup. No. No, that's
Oh no, life is over.
Shut up.
Life is over.
Shut up.
Oh, no.
He's gonna put soul on my-
You're gonna punch Annie?
Yes.
Does she have it coming?
No, not actually.
Does she? She has it coming. You can be honest.
Do you need help? Hey. Do you need help?
What is the mass for iron?
Oh god, it's 55.845. What did you get?
I got 55.844.
Whatever. Yep.
Yeah, that's fine. Isn't it so convenient that I wear my glasses just like you told me to?
Yeah.
I do actually wear my glasses, yeah.
Why don't you just get contacts? Do you have like insurance that'll cover it?
Maybe.
Because if you just don't like the feeling of glasses on your face, then it's better to get contacts. Daniel has really like thick glasses, like really thick glasses, and he switched over to contacts, and he stopped getting headaches. Yeah, because like they were thick. Cause he's short-sighted. He's nearsighted or farsighted, and then yeah.
How we doing? Excellent. Would you like words of encouragement?
No.
You sure?
No.
Angela, I think you're doing great. I think you're probably going to get the answer exactly right. I'm so proud of you.
I just said no.
You're welcome. I do think you're going to get the answer. There's nothing sarcastic about that. It could have made it sounded sarcastic because I prefaced it in sort of a sarcastic manner, but I've been told that my sarcasm and my sincerity sound exactly alike, which is problematic. All right. How'd it go? What would be a good sign that you might have gotten the right answer? Okay, A, if you have a periodic table, it should roughly match up. We shouldn't expect it to be perfect. I think this one does match perfectly because we dealt with all the major isotopes here. But that would be a good one. Even if you didn't have a periodic table, what would be another good hint? Just looking at the information we know, what is this going to be closest to? Yeah. Good, which is in this case iron 50, iron 56. And iron 56, by the way, note this annoying thing where note how that's a little bit under. That's that quantum effect we're talking about, right? We would expect this to be like 56 point something, right? And it's 55 point something, even though protons weigh 1 and neutrons weigh 1. That's that Einsteinian relativistic equals mc squared bit. That's the part where you just have to, at this stage in your career, say, okay, I can live with that. I accept that that's true. And then if you go on to study what we call modern physics, or sort of like quantum model, and start learning about these mass and velocity interactions, you'll be able to do the math that shows you why it weighs that. But for now, you just kind of got to be like, oh, iron 56 actually weighs a little less than 56, and just go like, yeah, okay, whatever. Is that fair? One thing about science is we kind of teach it to you in the order that we discovered it, mostly. And so just like when we were discovering it and we were going, hey, some of these things don't quite add up. They don't quite work. As we teach it to you, some of the things we teach you don't quite add up and don't quite work. And that led scientists to know, hey, there must be more we need to figure out. And that should lead you as a student to know, hey, there must be more they're not teaching me yet. And I try to avoid the thing where I just straight up lie to you. And I try to make a habit of pointing out when things don't quite make sense. And just say, like, just trust us, it'll make sense later. For example, my grade 12s are about to learn that everything I'm teaching you this unit isn't actually true. But it's true-ish. It's true adjacent. It's true enough. You know? It's true enough for now, until it's not true enough. All right, so if we want to find the average mass, I do not want to do this in red. If we want to find the average mass, what do? I take the sum of the mass multiplied by the abundance. All right, so the average mass then is going to be, and I've just got to go isotope by isotope. First isotope, iron 54. So with that, I can say the mass is 53.9396. And I'm going to use this mu for atomic mass units because you will see both. So I want to get you used to both. And what's the percentage on that? 5.85 out of 100. Again, if you prefer to convert that to a decimal, go nuts. Not how I like to do it, but who says you got to be like me? Nobody. Nobody says you got to be like me. That's who. What about this one? What should I write there? Yeah, so the mass is 55.9349, and this is our most common isotope. Oh, I forgot a unit. And listen, I am an absolute stickler for units in calculations. In math class, you've probably gotten in the habit of ignoring units and then just tacking it in at the end. It's not how we do it in science, all right? And later on in this course, you'll see why. It does make a difference, but yeah, don't cheat the system. And what's the abundance there? 91.75. And if I multiply it by 91.75, that's going to be a huge problem. I need to multiply it by 91.75 out of every 100. Does that make sense? By the way, this just takes care of the step where we divide by how many. Instead of doing it at the end, we do it for each one. Does that make sense? Remember when we take an average, we add them all up, then divide by how many? Well, each time we're dividing by how many. So that step's already done. What's the next isotope? It is indeed 56.9354. Wish I had my glasses right now. And that's multiplied by 2.12 out of 100. Good. And our final isotope. We're so very close, team. What color haven't I used yet? I haven't used a green yet. Oh, my computer's just crashing. Oh, interesting. In fairness, this started telling me like a week and a half ago I have an update to install, and I just don't have the time, so I've just left it running for, like, I haven't rebooted my computer in like 2 weeks. And so it's starting to behave strangely. I think it's definitely in need of a good reboot. So maybe today I'll take the plunge and reboot. And what is the mass of our last isotope? Yeah, 333. And that is multiplied by an abundance of only 0.28 out of every 100. So it's very uncommon, but it's still there. What do we do with all these? Add them up. And now, the most likely place to make a mistake doing this is just typing into your calculator, right? This is going to be overwhelmingly the most likely place to make an error. So we'll just go kind of, oh God, we'll just go kind of stop. Just stop. Honestly. 53.9396 times 5.85 over 100. Again, with that bracket that's doing absolutely nothing, but feels, you can even put this in brackets if you want. Is that bracket doing anything? Nothing. Does it maybe make you feel more secure? Then do it. 56.9354 times 2.12 out of every 100. And finally, 57.9333 times 0.28 out of every 100. And when we do that, what do we get? 55.845. How's that compare to what the periodic table tells us? Matches. Good. That's a good indication we did it right. But just as importantly, it's closest to this one and a little bit below it, which makes sense because the second most common one is below it, not above it, right? Does that make sense? Our number makes sense. It's good. We did good math. So we could say the average mass of an iron atom. I probably should have said that all the way along. You'll see, by the way, this convention where we put a subscript to say what we're talking about is something we do a lot in chemistry, because in any given question we might have a mass of iron but also a mass of chlorine and also a mass of oxygen. So if we just put down here what we're talking about, it avoids mistakes. Does that make sense? Cool. And what number did we get? 55.845. And what's the unit? Yeah, and the way I've written it is with that mu, and a reminder that mu is the symbol for AMU, which of course stands for what? Atomic mass units. Which is just really small. It's like 0 decimal and then like 24 zeros and then like 3, I think, grams. It's just a real small number. Okay. That's it for me today. Look at that. So you got some time to complete the practice here, probably plenty of time to get it done. Once you get that done, you can do whatever you like, but I'll remind you, in my class I don't like to see phones, so whatever it is you're finding to do, find a way to do it that doesn't involve being on your mobile device. And if you have